Hello and welcome everyone. So we're going to be talking about statistics today. This is going to be kind of a longer video in some respects, but then in other ways the material is going to move very quickly. So be ready for that pause button. So we're talking about statistics. We've already talked about it in class, but just in case, we're going to be going over it again. I'm also going to bring in the idea of tolerance. So I'm going to go through the slides, but then also I'm going to work some of the statistical examples in separate mediums, and they're all going to be in on this video, so that way you can see things happen in a little bit more of an active fashion. So this is not a statistics class, so I'm not going to go into the data a whole bunch. This is just more of can you calculate it and how do you calculate it sort of thing. So let's get started on this. So we're still talking about collecting and processing information, and that we can use computers to we can use computers to do this, because data and looking at data is part of the engineering design process. Now I'm going to go through this in multiple iterations. I don't know if you can see at the bottom of my screen, but you'll see that not only do I have the web browser up where I'm going to go and use Desmos, but I also have Microsoft Word and Microsoft Excel. So I have a Word document and I have a spreadsheet. So we're going to take a look at what does it mean to do this by hand, what does it mean to utilize tools like a spreadsheet, and finally using just a full-on computer program. So data is used throughout the engineering process to optimize designs and improve efficiency during productions. So this idea of optimizing design and improve efficiency, you're just going to hear me refer to it of make a product better, because this is a very wide array of things. Statistics refer to the collection and organization of data, as well as the analysis and presentation of those data. And so when we look at collect data, that is usually kind of a scientific element. That is research and things like that is kind of how they're wording this. Whereas actually doing the number crunching and interpreting those values and what they mean, that is the mathematics element of collection of data, collecting data. Okay, statistics are often evaluated using the assistance of computers and software such as Microsoft Excel. I'm going to be using Microsoft Excel today. Such tools allow the use to easily access, collect, organize, maintain, manipulate, and interpret data, which helps improve efficiency. Okay, when I work out the problems kind of step by step in Microsoft Office, and then I show you how you can do things in Microsoft Excel and then also in Desmos, you'll understand why we use the computer programs. Okay. Basic statistics in engineering include the following terms. So these are what are called methods of central tendency. They are the mean, the median, and the mode. Where the mean is the average. This is the arithmetic mean, is the average. The median is the number that's in the middle whenever you order a data set. The median is the only one where the information has to be ordered. The rest of them you can kind of work your way around it, but they become harder to deal with if the information is not ordered. And then the mode is the number that occurs most frequently. In a normal set of data, kind of when there's nothing unusual about the set of data, usually these three are going to coincide or be pretty close to one another. But that is not always the case, and it's part of the reason why we have three different methods of central tendency. The others are measures of spread. So we have two measures of spread here. The standard deviation, how much variation exists from the average in a given data set. Kind of think about it in terms of average spread. And then the range, the distribution of data of the data set, or the difference between the largest and smallest values. This is the term that we use the most, which is you find your largest value, you find your smallest value, you subtract the smaller from the larger. Now we also have this element called tolerance. And when you think about tolerance, tolerance in my opinion at least, kind of has a little bit of a negative connotation to it. Because when we talk about tolerance, usually we're not talking about necessarily the nicest thing. But if we look at tolerance in terms of a social setting, it just, I like to word it as you may not necessarily agree, but you still would consider it within an acceptable range. And in engineering, math, physics, and those kind of things, tolerance has a similar element to it. The amount of the amount, a characteristic, product, part, dimension, whatever, can vary without compromising the overall function or design of the product. And it greatly influences the basic statistics used in manufacturing. So in other words, if I were working on a project, and let's say something that I needed something 2 feet in length. What if it wasn't exactly 2 feet? What if it was just a little bit over? What if it was a 1/16 of an inch over? Is that okay? What if it was a 16th of an inch under? Is that okay? And for most things, we would say yes. But what if it was, 2 feet 1 inch? Or what if it was 1 foot 11 inches? That's probably not okay. And so that's outside of the tolerance. And so these are the ideas of tolerance. So some basic terms with tolerance that you need, that you would want to know. The normal size, or the size used in the general description of the part or product. So whenever I come out with a design and I say it needs to be these dimensions, that's what we're talking about with the normal size. The basic size is the converted normal size, fraction to decimal, that can produce some deviation. So if you have ever heard somebody say this needs to be 2 feet plus or minus 1/4 of an inch, that they are talking about the basic size there. The upper specification limit is the highest acceptable deviation or value for the characteristic, and the lower specification is the lowest acceptable deviation. So again, when I say if somebody ever talks about something plus or minus a particular value, the upper specification is plus, the lower specification is minus. So if I said you need to score a 60 plus or minus 10 points in order to reach your target, the upper specification is 60 plus 10, which would be 70. And then the lower specification would be 60 minus 10, which is 50. So let's get into some actual values and some symbolic logic here. Well, not really symbolic logic. That is something specific in math, but the symbolic notation. Okay, there we go. All right, so if we use X to represent the data set, this is uppercase sigma, but it's kind of the funny looking E. That means sum, and N is the total number of values within the data set. Then for the mean, it's sigma X divided by N. So in other words, you sum up all of your values, and then you divide by the number of values in the set. So given the following data set, 1, 4, 4, 6, 7, 8, 10, what is the mean? So you're going to take these values, you're going to add them together, and there are 1, 2, 3, 4, 5, 6, 7 values. So then you're going to divide by 7. So you add them all together. The sum of those is 42, and the number of elements in the set is 7. So then it's 42 divided by 7, which the mean is 6. Now the thing about the mean or the average, in this case, the average existed within the set. But that's not always going to be the case. In class we've worked on means where the number that we get for a mean does not actually exist in the set, and that is okay. That is okay. The median is the middle number in the set. So, but again, the median, you have to order the data set. So 1, 2, 3, 4. You look for the number. You look for the number that's in the middle. If it's an even number of elements, then you're going to have two numbers. You're going to have two numbers in the middle, in which case just take the average. Take the average of those two numbers. So 2 plus 4 divided by 2, and so that's going to give you a result of 3. So try this one on your own. What is the median for this data set? If you have not tried this on your own, you may want to pause the video now just to give yourself the opportunity to do so. But to find the median, first thing, order the data set, and then look for the number that's in the middle. You may want to do something like, scratch through the 1 and the 12, and then the 4 and the 8, the 4 and the 7, and then that's going to leave you with the median 6. There are mathematical approaches to this, such as, okay, so there's 1, 2, 3, 4, 5, 6, 7. So if I take 7 and I cut it in half, that's 3 and a half. there's a rule that essentially says that when it's even, then you're going to take that number, the next number, average those together. There's if you get a value like 3.5, you round up, it's going to be the fourth term. But again, this isn't a math class, but there are more efficient ways to find those numbers. But you still have to order. You still have to order the data set. So what's the median? What's the median for this set? There's 6 elements, and so then when you order them, you're going to find that it looks like 4 and 6 are your 2 middle terms. Average those together. 4 plus 6 is 10. 10 divided by 2 is 5. So notice in this case the median does not actually exist within the set, and that is okay. That is okay. That kind of stuff is going to happen. The mode is the number that occurs the most. In this data set, 4 occurs twice, where everything else occurs once. For our purposes, the only time that we are going to say that there is no mode is if every number only occurs once. Every number if every number occurs only once. Otherwise, it's going to have a mode or multiple modes. Okay, that's for our purposes. All right, what's the mode? Which number occurs the most? It's going to be 4. You don't have to order a set to find the mode, but when you get into larger data sets, it may help you count the numbers a lot faster if you were to order them. The standard deviation. The standard deviation, which I abbreviate mine STDEV, because in a lot of computer programs, that's the abbreviation. And in Desmos, as well as Microsoft Excel, STDEV is the abbreviation. So for this slide, they use SD, but when I move on to mine, I'll use a different abbreviation. And just be mindful of that. Okay. The standard deviation is a unit. It's something that holds value. It's used to measure how weird something is. It's used to measure how spread out something is. Okay? Just to give you a quick example, let's say that I do test scores. Class A has an average of 70. Class B also has an average of 70. Class A has a standard deviation of 10. Class B has a standard deviation of 20. What that would mean is that Class B, some of the scores go higher, but also they go lower than in Class A. That's kind of so it helps tell us on average how far things are spread apart. And so that's kind of what they're talking about with the weirdness here. Things that equal the norm measure 0 standard deviations. And so when we're talking about the norm, most of what we are going to deal with is what's called a normal distribution. And so the mean, the median, and the mode are all the same. So we're saying average. Things above the norm measure positive standard deviations, and things below the norm measure with negative standard deviations. We, again, are not going to go too much into that. We're more concerned about what is the standard deviation. Okay? Understanding the standard deviation. When you construct something, you're going to have error. Okay? It does not matter how hard you try. You're going to have some error. So, all right, let's say I have a relatively skilled crew. They build 100 bridge pilings according to certain specifications. There's going to be some wiggle in the height of the pilings. Some are going to be a little bit taller. Some are going to be a little bit shorter. On the average needs to be really close to the specification. Okay, I mean we're talking, hundredths of an inch, or in this case millimeters. You're talking within a millimeter or two, or even more specific than that. Okay, but so you want your average to be what the specification is. All right, so now we set a tolerance as to what a good build is. You know, we determine, let's say that these pilings need to be plus or minus within 2 millimeters. You know, that might be a good goal. I don't know exactly what they're doing, so you know, I can't say for certain. But you do want accuracy, but it costs too much to be super duper accurate. So in some circumstances, being within 2 standard deviations of the norm is good enough. Okay, so that's the use of the standard deviations. Long story short, 95% of data typically falls within 2 standard deviations. So, okay, that's okay. If these pilings are holding up a bridge that needs to carry the space shuttle to the launch pad, you may want the piling to be half of a standard deviation. So that's saying there are certain situations where you may want the accuracy to be even closer. Standard deviations are what we sometimes use to help us measure or to help us decide what acceptable tolerance is, if that makes sense. Okay, when a new piling is built, you measure it, you convert the height into its range with the standard deviation, and then you decide whether or not it's within tolerance. If it is, great. If it isn't, you tear it down and you rebuild. Okay, so we use standard deviations to help generate the tolerance. And then once we know what the tolerance is, we know the acceptable range, and then we say, is it within the acceptable range or not? Okay, so how you calculate the standard deviation is you take each element. From that element, you subtract the mean, and you do this for all of them. Then you square all of those values. Then you add all of those values together. Once you do that, you figure out the number of elements in that set. Take one less. So if there were 15 elements in the set, you would go to 14, and you would divide by that number. Once you do all of that, then you take your square root. Okay? Now the thing about this is not the formula that I used in class. It is the same formula, but it's not the notation that I used in class. Instead of using this kind of weird looking U, which is actually pronounced mu, we used X bar. We actually used X with a bar over top. Okay? It means the same thing mostly, but if you get into a statistics class, that's going to be a big deal. Okay? So don't pay attention to the format, not necessarily to the specific letters that they use. When I do this in Word, I'll use the formula that you want to use. Okay, so what's the standard deviation for the following data set? So we have 1, 4, 4, 6, 7, 8, and 12. First thing that you would do, or the first thing I would do, is I would count up the number of elements. I count up the number of elements. There's 1, 2, 3, 4, 5, 6, 7 elements. So this n minus 1 becomes 7 minus 1 over 6. Next thing you would do is you would find the average. You would find the mean of all of these, which was done in a prior slide. It turns out it's 6. Then you take each element, 1, subtract 6, 4, subtract 6. There's another 4. Then there's the 6. Then there's the 7. Then there's the 8. And then finally there is the 12. Okay? 1 minus 6, that's a negative 5. Then you're going to square it. When you're doing this in a calculator, make sure you square the negative. All of these numbers should be positive. So 1 minus 6 is negative 5. Square it, that's 25. 4 minus 6 is negative 2. Square it, that's 4. Do it twice. 6 minus 6 is 0. Square it, you get 0. 7 minus 6 is 1. Square it, you get 1. 8 minus 6 is 2. Square it, you get 4. And then finally, 12 minus 6 is 6. Square it, you get 36. Add all of these numbers together, you get 74. And so when you input that, that summation takes care of everything in the numerator. So then this becomes 74 divided by 6, which is 12.3 approximately. Take the square root, you get 3.51. And so that would be your standard deviation. We'll look at some data sets here in a little bit. Okay, the range is just what's the difference between the largest and the smallest. So in this data set, there's 5 elements, but I don't even need to know, not for range, how many elements are in this set. I look at the maximum value, which is 4, the minimum value, which is 1, and then I subtract. 4 minus 1 is going to be 3. So what's the range of this following data set? Maximum is 12, minimum is 1, and so you're going to get 12 minus 1, which is going to be 11. Okay, so engineering tolerance, the amount of characteristic the amount a characteristic can vary without compromising the overall function of the design or product. So we see tolerance in a lot of different areas. The common ones, physical dimensions, so part, fastener, coupling. You need a pipe, and that pipe needs to have a certain diameter, but it's not going to be 100% exactly that diameter, so it needs to be in between a range. At its largest, it can be this big. At its smallest, it can be this big. Physical properties, materials, services, and systems. So how strong a material is could be one of them. How much a material weighs could be another one. Just lots of different things. And then calculated values like temperature. I take I have to take medication, and those medications all say store within, and then there is a temperature range. There is a temperature range, between 50 and 100 degrees. And if you go to the store and you look at pretty much any medication, if you look around long enough, you're almost always going to find a tolerance of what is considered acceptable temperature. Engineering tolerances are expressed like a written language and follow the American National Standards Institute, ANSI, standards. There are some other standards that are out there, but they all kind of follow the same. They all follow the same thing. Okay, bilateral tolerance. Now, this isn't all of the ways that you're going to see it, but they are there. Bilateral tolerance, where they just tell you. They may tell you what the ranges are. They may tell you the maximum and the minimum, or they may write it in such a way that it's that it shows up in 2 points. Unilateral tolerance. The upper and lower specification limits are derived from acceptable tolerances, and that's often where the standard deviation has come into play. Bilateral and unilateral are just 2 examples of how tolerance is expressed using ANSI standards. Okay, there are other ways to do it, but these are going to be the ones that we focus in on the most. Okay, so what are the upper and lower specification limits in these 2 examples? Okay, so I have 1.125 plus or minus 0.025. So 25 1,000ths of a measure. And so the upper specification limit, you just add 0.025 to this one to this number. You're going to get 1.15. The lower specification, you're just going to subtract that number from this right here is probably the mean. Now, I can't say specific because I don't know exactly where they pull these numbers from, but that is the general assumption. It's either the mean or the design constraint. So when I subtract these 2 numbers, I get this new set of numbers. And it could be listed as a range, because for whatever this thing is that has these particular values to it, as long as my result is between 1.15 and 1.1, I'm good. The range should be equal. The range should equal the difference between the upper and lower specification limit. So when I subtract 1.1 from 1.15, I should get 0.05. The other thing about this is just a quick check. The range should be twice that, twice the tolerance. Okay, so here's another one. Here's an example of the unilateral tolerance. But it's the same thing. I take my constraint, 2.575, and I add tolerance. That's my upper limit. That's going to be my upper limit. I subtract. That's going to give me my lower limit. The range, if I subtract the smaller from the larger, is 0.01, which is twice the 0.005. Okay, and this is where some of these different values came from. So I'm going to take a look at two different data sets. I'm not going to worry too much about the tolerance on these for now, but we are going to look at how to calculate the mean, the median, and the mode. So that way you can see this in a slightly more dynamic fashion instead of the static PowerPoint slides. Okay, so I want to take a look at two separate data sets. I'm going to work these out by hand, and then we're going to go to Excel, and then we're going to go to Desmos, and just show you, there's pros and cons. There's pros and cons to every one. The pros of working it by hand is you get to really understand where the numbers come from. So usually we start off by doing the mean first, but I'm going to start off with the mode because that's the number that's going to occur the most. So when you look at this data set, which is 1, 1, 2, 3, 3, 3, 4, 5, 5. 1 occurs twice, 2 occurs once, 3 occurs 3 times, 4 occurs once, and 5 occurs twice. So the mode in this case is going to be 3. When I look at the median, so I'm going to do just a real quick copy and paste here, and I'm just looking at. I'm going to take away the first value. I'm going to take away the last value. I'm going to take away the last value. I'm going to take away the first value, and it becomes apparent pretty quickly, which one of these it's going to be. So the median in this case is also 3. Now in the next one, the mean, I just want to go ahead and clarify, because also I need this value in for the standard deviation. So there's 1, 2, 3, 4, 5, 6, 7, 8. There's 9. There are 9 values in this data set. So now I'm going to calculate the mean, which, if you remember the notation, this just means you add up all of the elements in this set. So I did a little shortcut here and already had this ready. So this is going to be 1 plus 1. The third element is the 2. The fourth element, the fourth, fifth, and sixth elements are all 3s. The seventh element is a 4, and the 8th and 9th element are 5s. And then this is just divided. By 9. So now I'm going to start adding these. I'm going to start adding these together. 1 plus 1 is 2. 2 plus 2 is 4. I'm going to 3 plus 3 plus 3. That's 9. 4 plus 9 is 13. 13 plus 4 is 17. 17 plus 5 is 22. And then 22 plus 5 is 27. And then finally, 27 divided by 9, that's going to be 3. So the mean in this case is 3. The range is just going to be the maximum, which is 5, minus the minimum, which is 1. And so the range is going to end up being 4. And then the standard deviation, as you can see, there's a lot of room here. There's a lot of room here. This one takes a while. This one takes a while to calculate. Okay, that's just to do this by hand. So I'm going to take each element I'm going to take each element, I'm going to subtract the mean, I'm going to square those values, I'm going to add all of those together, and then I'm going to divide by n minus 1. So instead of doing this in the exact order, I'm going to go ahead and take care of that n minus 1, because I don't divide by 9 and then subtract 1. If I do, that's going to give me a wrong value. I subtract 1 from 9, so I'm going to divide by 8. The mean in all of these cases, everything, I'm subtracting 3. Now, let me see if it lets me. Here we go. All right, so I'm just going to, in all of them, 3. All right, so I'm subtracting by 3 in every single one of them. If it happens to leave the bar, I'm not going to worry about it. So you can see the setup in this takes a while. The setup in this takes a while, and this is why doing these in like a spreadsheet or something is going to be a lot easier. Okay, then I combine each of the elements. Okay, so if I go back and look at the list, there's 2 1s. So 1 and 1. There's a single 2. There's 3 3s. 1, 2, 3. There's 1 4. And then there's 2 5s. So now I go and take care of each of these computations. Okay, so let me go back to the beginning. Okay, 1 minus 3, that's negative 2. 1 minus 3, that is a negative 2. 2 minus 3, that's a negative 1. Now, in reality, when I do these, I actually just go ahead and take care of everything at the beginning. But so like I would do 3 minus 3 is 0, 0 squared is 0, and I would do it that way. But I'm going in order. 3 minus 3 in each of these cases is 0. 4 minus 3 is just 1. And 5 minus 3 is 2. And 5 minus 3 is 2. Okay. So now that we have all of that, we're going to square. Negative 2 squared is 4. These should always be positive. Negative 1 squared is 1. 0 squared is 0. So that's going to be true for all of them. 0. 1 squared is 1. 2 squared is 4. And 2 squared is 4. So, hopefully you can see that at this point, the calculations by themselves are not anything incredibly difficult. But it is repetitive. 4 plus 4 is 8. 8 plus 1 is 9. 9 plus 0 plus 0 plus 0 is just 9. 9 plus 1 is 10. 4 plus 4 is 8. And so 10 plus 8 is 18. 18 divided by 8 is going to be 2.25. And so then the square root, and I have to, I don't have to, but I'm going to change up my symbols here. The square root of 2.25 is, oh man, no, this is totally by luck, but it is exactly 1.5. It is exactly 1.5, and so then that's going to be my standard deviation. Okay. So that's your process. I'm going to zoom in so that way you can see a little bit better here. This is the formula that you need to use for standard deviation, as opposed to the one that's in the notes. Okay, so let's take a look at another data set. One of the differences between this first one and the second one is obviously, obviously the numbers are different, but this one was not. This one was not already given in descending order. So I look around. I look for the two smallest values. In this case, there's two smaller values, which is the 25. So I'm going to get rid of those. I'm going to get rid of those here. I look for the next smallest value, which is 26. Next smallest value, which is 31. And then from here, I can see pretty easily it's going to go 31, 37, and then 40. Okay. All right. So is there a mode? Yes. 25 occurs twice. All of the other numbers occur once. Okay. The median. I'm going to take this list. I'm going to take this list and then start, eliminating. So there's my first and my last. I've got a new set. So I'm going to eliminate my first and my last. I'm left with two. I'm left with two values. So the median is now the average of those two numbers. So 26 plus 31 divided by 2. 26 plus 31 is 57, and then divided by 2. So I am going to get 28.5 is going to be the median for these. Yes. There are 1, 2, 3, 4, 5, 6. There are 6 elements. There are 6 elements now. So we go into the mean, and I'm going to now just use, I rewrote my set. There's nothing wrong with that, and I'm just going to use these formats. 25, 25, 26. So I will be honest, which is the prior set I designed specifically to come up with like nice clean numbers. I didn't do that. In this case. Okay, so now let's start adding the numbers. 25 plus 25 is 50. 26 plus 31, we've actually already done that calculation. That's 57. 37 plus 40, that's going to be 77. Okay. 50 plus 57, that's going to be 107. And 107 plus 77 is going to be 184. And then 184 divided by 6 is equal to, and this becomes an approximate, I'm going to round, 30.67. Okay. The range is just the largest value, which in this case is 40, minus the smallest value, which is 25. And so with that, you get a range of 15. I'm gonna come back. I'm gonna set up the standard deviation here momentarily. Okay, so let's take a look at the standard deviation. We have 6 elements in this set, and it's again, it's actually the calculation is not going to be anything too difficult. So I went ahead and set everything up and pre-input the numbers to make this a little bit easier. But the work is by itself not incredibly difficult, but keeping track of the numbers, it's just kind of time-consuming and repetitive. So I've expanded the standard deviation equation so that way it contains all 6 elements. I then start inputting those elements, and you can see that the equation actually gets long enough that it hits 2 lines. So I added in the mean, which was 30.67. Now that was approximate, so automatically technically speaking, we no longer have the true standard deviation. We are already at an approximate because the mean was not 30.67, it was 30.6 repeating. Okay, so this is rounded. There were 6 elements, so I'm going to do the 6 minus 1. I input the individual elements into the equation. So there was the 25, 25, 26, 31, 37, 40. 6 minus 1, of course, is going to go to 5. I then subtract the mean. From all of the original elements. 25 minus 36.7 is negative 5.67. Negative 5.67. 26 minus 30.67 is negative 4.67. 31 minus 30.67 is 0.33. 37 minus 30.67 is 0.633. And 40 minus 30.67 is 9.33. Next, I square all of those values. So I get 32, 32, 21, 0.1, 40, and 87. Now, the thing about this technically here is these numbers are accurate based off of the prior numbers, but there is an included error because the mean is not actually 30.67. Okay, so we can actually flip-flop back and forth between approximate symbols and equal symbols, but that's that's nitpicky here. So I'm just leaving everything as equals. I add all of these numbers together, and I get 213.334. Finally, next I divide by 5. I get 42.668, and then finally take the square root of that, and I get approximately 6.532. And so those are the numbers that we're going to get. I'm going to show you how to do the same calculations, same style, but how something like Excel can do this much more efficiently, and also help us determine the median and the mode in the next part of this video. Okay, so here I'm going to use Excel, and the thing about Excel is I'm going to show you just a couple of different methods. Just here very quickly show you the power of using some tools like this. I'm not going to demonstrate the coding and go back and all of that, because guess what? You can pause the video so you can look at it then. But I am going to move through this rather quickly. So here's that first data set, 2 ones, 1 2 3 3s, a 4 and 2 5s. So I want to calculate the mean, the median, and the mode. Well, I can compute it. I can count the number of items. I can count the number of items in the cell. That way, I can utilize something called the sum function, which allows me to input all of these numbers. And then the average was just the sum of the elements divided by the total number of elements, and so then that gives us our average 3, which is what we got. There is also a mean function. There's also a mean function, and not mean, average. There we go, that's better. And so then that gives us the same number. And there is also the median function, and there is a mode. There is a mode function. I can use a maximum. I can use a maximum function to help me calculate the range function. I think there may be actually a range. I think there may actually be a range function, but I'm not entirely sure. But the range is just the maximum minus the minimum, so I get it that way. I can utilize the definition of the standard deviation to help me come up with the various formula. So you square everything, then you total that together. You divide by n minus n-1. So I'm going to go ahead and bring that feature into this problem. And then finally you take the square root. And the thing about it is that if you know these codes, you know how to use a spreadsheet, then you start moving through these things. You start moving through these things very quickly, and you should see all of the numbers that we had when we were previously working out these problems. So there's, you see that 441000144. The total, remember, that's just summing everything up, and so it's not a coincidence, you know, that we use the sum function there. I'm taking that number and I'm dividing by n-1, which we said was 8, and then which is 2.25, which we saw again. And then finally, when I take the square root of that number, I get that 1.5. And so then I verify. Now, the thing I want to point out here is as I start typing standard deviation, you see there's a lot of different standard deviation function formula things that come into play. And which one you use when is not necessarily the easiest to come up with, but it's very quick, you know, to go through. It's very quick to go through all of these numbers. All right, so I'm going to do something else, because here's my next set. This doesn't make a lot of sense. This doesn't make a lot of sense right now, because I've had to move things around, because these aren't all the same. These aren't all the same sets, but actually it copies over quite nicely. So here's my count. I need to change this value. I need to change some of these values, but stuff starts to pull through rather quickly, because now instead of recreating everything from scratch, all I'm having to do now is modify, and that makes things a lot easier. Notice also that I don't have to necessarily have these in order. I don't have to have these in order anymore. And my numbers are matching. They're coming up nicely. We saw the 6.53 earlier. We get the same number when going through these calculations, and so just very quickly, just that quick, I've fixed, and I've come up with the second one. So in the next section, I want to show you how to do this in Desmos. Now, Desmos does not have the mode, but there is a way that we can get around it, and so we're going to talk about that in this next. Okay, so now we're going to take a look at this in Desmos and how to do this in Desmos, which again, very similar. So first thing I did is I went ahead and put both sets in there, and I gave the sets names, A and B. So they have 9 elements in the first, 6 elements in the second, so that is kind of what I was expecting. So now if I just want to know the average, I type in the mean, the median. I type in median, then I give the name of the set. Now, the mode is not something that we can do with Desmos, at least not now. So instead what I do is I create a histogram with the width 1, with bin width 1, and then I look for the one that has the peak, and that's going to be my mode. For the range, I find the maximum, I find the minimum, and I just subtract. So this is max A minus min. Okay, and so then there's my range. And then finally, for standard deviation, I just calculate the standard deviation. And now the really nice thing about this, couple of things, I don't actually have to order this now because the computer will sort it for me. If I want to find the mean of group B, I just change the group. There's the median of group B, and those numbers should look familiar. There's the histogram. Now my histogram disappeared because these numbers are not, 2, 4, 6, or 8. But if I go down here to the zoom fit, there it is. I see that is going to be my mode, which turns out to be 25. The maximum of group B was a 40. The minimum of group B was 25, so I should get 15 when I change everything over to B. And then finally, the standard deviation, 6.53.